Hi, good morning. My name is Miguel Pavon. Thank you for having me here at ATX GIS Day. A few months ago, I was invited by my boss to participate in a project. The project to support the flood decision support system by the USGS. One of the things that they needed was a Texas-wide collection of buildings. That may seem to be a simple enough to do thing, but it was a complex endeavor. Because they needed also a building valuation, the value of the buildings, not the parcels, and also possibly flood damages at different water heights. As you can imagine, that depends on the water height and the valuation of the building, and also depends on how the building is constructed. Here is some of the background. The USGS is in partnership with TWDB and the TNRIS to develop a flood decision support tool, also called FDST. The USGS will develop all the hydrology and all the tools, and TNRIS will develop all of the data layers for Texas. One of the layers needed is an initial valuation of the buildings. So we took two initial Texas-wide building layers. One is building from OpenStreetMap, OSM, that were generated by users, just like you, digitizing on the screen on top of imagery. And the other one, the Microsoft's Artificial Intelligence Buildings layer that was developed by photogrammetry. These datasets are public, they are free, and everybody can get a hand on them. The thing is, OSM works very well in city environments, where there are a lot of users, but in rural environments it was lacking some of the buildings. Microsoft AI works well in all over the state, but there are some data deserts. We will see where that is. So, here's an example of the Microsoft buildings. And you can see where they didn't have imagery in both stair pairs, we have data deserts. Here and there. In the rural or less developed areas, we have a good inventory of the buildings. But we still have to deal with the problems of having no buildings at all in these two pieces of land. On the other hand, the OSM buildings cover the data desert, but it's not as dense here in the hills. So what happens when we merge both of them? What happens is that we have some buildings that we gain over here, but we have many duplicate buildings. We have a lot of buildings that are mapped twice if we just merge them. Some buildings are just in one system and some on both. That begs for a GIS question. How do we solve that? We need to select some to find the gaps. So we do a spatial selection in which we use the OpenStreetMap buildings as our input features and intersect that with the Microsoft buildings to see which ones are covered by them. And then the thing is that you can invert the spatial relationship to see which ones are not. When you go and apply it, then all the buildings that are not covered by the Microsoft buildings are displayed here. So now the trick is to merge those with the Microsoft buildings, and then you have one building of each. You will have no duplicates. That is fine, but that is a high level view of it. What happens when you see it closer? Here are the Microsoft buildings closer. And when we invert select off the OSM buildings, we have new ones that we can use to improve our coverage. The result is a hybrid layer selected filling all the gaps. So we are going to work with this one. It is not perfect, but it's generally good all across the state, and it is a good thing to begin working with. There are some pros and cons. The pros are that it's publicly available. while complements urban and rural areas. It is already done by OSM and by Microsoft, so we don't have to do much work again. And it is better than having summaries by census blocks, so we can go all the way to the building level. On the cons, it is kind of dated. It is from 2016, 2015. We have still no assessment or estimation of the building values, and we do not know if a building is worth $100,000 or $2 million. We have not yet any damage calculations if flooding occurs, but that is something that we can solve. Because back in 2018 and 2019, TNRIS started acquiring land parcels, so we have the Land Parcels 2019 collection. There is a free resource that is downloadable at the TNRIS Data Hub, and here it is. It's not super big, it is like a 2.5 gigabytes and has all or most of the land parcels in the state of Texas. So, we downloaded that and now we can complement our buildings with some of the evaluations. What is the workflow? The workflow is to do a spatial join between the parcels and the buildings, keeping the count, because we may have several buildings in a parcel. If we have 2, 3, or 4 buildings, the value of improvement needs to be divided among all of them. We cannot assign the value of improvement to each building, because it will be multiplying the value. Then we can calculate the number of square feet per building and by type county when assessing the value of the improvements. That will allow us to get the square footage and the price per square foot per building and per county, because the square footage value of a building in Milan County will not be the same as some in Travis County. Then we can concatenate the building type and the county to have a unique identifier by building type county and create a table summarizing the building type county. That table was almost 4,000 unique rows of building types counties combinations. With that table we can calculate the average square footage, the average price per square footage, and price per building in those categories. Then for the buildings that do not have an assessed value, we can calculate it. With the square footage, the number of floors, and the price per square footage, we can calculate the value of the improvement, multiplying the number of stories by the square footage by the price per square footage. Then, since we have too many building classes, we can simplify it into fewer classes, like 5 or 6. For example, commercial, industrial, residential, and so on. And then we can assign damage curves based on the building type, the number of stories, and if they have or not a basement. Each curve will have different damages per flood depth. Then keep only the relevant attributes that we need to have and share that with the USGS. So that sounds good in theory, but the devil is in the details. When we see the Texas area parcels and we see the value of improvement, all the parcels in gray do not have a value of improvement. It is null. So the assessed improvement value is either something shown in yellow, orange, and red colors, or it is null in the gray colors. So the assessed value is null, and that is okay for now. We can fix that. If there is a building used for religious purposes, normally it is not taxed or appraised. The value for this and other buildings is not calculating, and that is okay. No need to panic. When we did our summary table, we did it by type of building and county. So we have, for example, single-family residence for Harris and for Dallas and for Bexar counties. So we can calculate what is the mean improvement value of that, what is the mean square footage, and what is the mean price per square footage for buildings in Harris or Dallas. Those may be more expensive than buildings in El Paso County, for example. But now we have one estimation of the mean price per square footage by improvement type and by county. We can use that to calculate all the assessed improvement values that are null. To do this, it is important to exclude the records with an assessment improvement value already. We have to select only the ones without valid values. So once we have our summary table, we can link it to the feature or buildings table. And then we can estimate the improvement values based on the price per square foot and the number of square feet that we have. To track our steps, what we did is to have the assessed calculation for the ones that already have a value as assessed and the ones that we calculated as estimated. That means if we discover that something is not right, we can go back and trace our steps. We can see if there was something wrong in our calculations or if we need to rethink our steps on what we did. So we only calculated those that previously had a null improvement values. Okay, that covers the evaluation for all the buildings, almost 10 million of them. All of those have an assessed value now. And that was a significant step, so we are able to calculate values based on the appraisal district from the CAD or an estimation based on the number of dollars per square foot and the number of square feet of every building. That was significant. I feel happy about it. But that was just part of the solution. The other part is to calculate the potential flood damages. And for that we have damage curves. We use 6 different damage curves. This is an example for single-family residence, 1 story and no basement. Most of our buildings were single-family residence, 1 story and no basement. So if one happens to have 1 feet of water, flood water, then we have an estimated damage of 23%. 23% of the building is damaged. We are not talking about the contents, just the building. For example, replacing sheetrock, electricity, insulation, etc. Materials have to be dried and treated or replaced. That is a significant amount of work and a significant cost. As we go past 10 feet of water, 70 or 80% of the building is damaged. Pretty much the whole 1 story is underwater. And more water on top of it is not going to contribute significantly to more damage. But we calculated damages all the way from 1 through 16 feet because different damage curves may not taper at the same points. Imagine calculating 10 million records times 16 columns plus some of the other attributes that we calculated. Like the calculations we did before, that is almost 250 million calculations. That is a lot. And this is an example of the table, some of the damages that we calculated if you have a basement or if you have a number of stories. If you have a null, you need to infer no basement and only 1 story. And then the type of building, single family residence, and so on. So as we go through the table, we can see that we calculated damages at depths from 1 feet to 16 feet of water, and that we kept track of which damage curves we use. 1 story, no basement, single family residence was the most common type. But sometimes we can have a structure with 1 story, no basement, or 2 or more stories with no basement. In few cases we have structures with basements, and we use different damage curves for all that. And here on the simplified type, in the view we have mostly residential buildings. Okay, so that data is part of the iteration for these buildings calculations was done. We did some QA/QC. We went to places that we knew, for example, my house, and we see that what is the valuation to my house, if that makes sense. Then, how is that going to dovetail into the USGS flood decision support tool? This is an initial view of the FDST. You have different places in the state where the hydrology has been calculated. This happens to be East Austin. You can see the Colorado River, and there is a stream gauge with a marker. So what USGS is doing is to run hydraulics to see what happens if you raise the level of the water, the height of water at the stream gauge, the size of the flood. At 40.5 feet, all these areas are covered with water, and water at different depths is shown in different colors, respectively oranges to dark blue, from 1 foot to more than 9 feet of deep flooding. You will notice that there are areas outside of the study area, and that the study area is limited by those yellow lines. So, no water here does not mean that it's not going to flood. It is just outside of the study area, like where it cuts off over here. When we show the buildings layer, it is placing some of the buildings inside the flood polygon, and then we can calculate if they are on 1 foot of water or more and estimate the damages. This is an artist's rendition of the final product that will look something like this, where we have a total number of buildings on the water and an estimation of the total damage, total cost to fix all of the buildings, but that will be in the future. We are hoping that by January, both the USGS and the Texas Water Development Board can have a joint announcement when the first phase of this product is ready. We are still working on that. But I mentioned that the buildings were just the first iteration. Why? Because some of the counts, that they are dated, that they are from 2016. We have some LiDAR datasets that are newer than 2016. So next steps include to update buildings with LiDAR-derived footprints. So if the building was demolished and renewed, or if people added to it, we can follow this recipe that we have presented for your review before, to create new building footprints and follow the same inverse spatial selection to update with LiDAR our initial building layers that we created with Microsoft and OSM buildings. So explain briefly, to do that we check that the LiDAR collection has buildings as a class so we can work with it. Quickly we will go over creating building footprint polygons. We use LP360 for that, and now every building has a yellow footprint. We can see the Long Center and some of the buildings in downtown Austin here. We can create a digital elevation model for the ground. We can also create a digital surface model for the buildings. Subtract the DEM from that to create a normalized digital surface model with just the building heights on it. From there we can estimate the number of floors that we have. So ArcGIS Pro has a tool called Extract Roof Form that you can download from ESRI, and that calculates the roof form from the footprints and creates a three-dimensional models for the buildings. In some areas will be mostly one-story houses, and in downtown Austin mostly multi-story buildings. From this approach we cannot estimate if you have a basement or not. So they assume they don't unless the appraisal records show that they do have a basement, so that we can use the appropriate damage curves or damage functions to estimate damages, to calculate the flood damages. Every building here is a record on the table. So you can come here, and if you know something is wrong, for example, if this roof in blue is not flat, it is more like a dome, you can change it here in one of the attributes, in the roof form attribute. And eventually it will look something like this. This may be the next step, but we are not there yet. We are hoping to update our buildings layer every 6 months or so. Extracting information from the data takes time and resources, but is very useful in emergency situations or to make decisions. Also to plan multiple scenarios with digital floods and develop mitigation strategies. So, about how long will this take? This is just a calculation for one portion of one LiDAR collection. This collection has 10 portions. If we can process 1,000 LiDAR points a second, with this many data points in a portion, it will take about 12 days to process all that. That is a lot of time. We can do it faster with multi-threaded parallel processing. If we have 8 cores, instead of taking 12 days, it will take only 1.5 days. This is a final result for Houston area. We can see a different collection, just an example. Here is another example, the University of Texas at Austin using multi-patch shapes, part of our database. So with these buildings we can update our inventory about twice a year and try to keep it fresh. In 2021, we will have a complete LiDAR dataset for the state. We need to work on classifications. And after that, we may have in 2022 a complete inventory of buildings updated for the state of Texas. Then we can repeat the workflow shown at the beginning, update the buildings, calculate their values, and apply the damage functions. With all the other attributes, make that accessible to USGS so that calculations can be refreshed and also more precise. With that, this is all that I have to present to you today. I hope we can open the floor for questions, and hopefully I will have some answers for you. Thank you.